Welcome to a bit of an intro video on the topic of rational functions. Rational functions is a type of idea where we have a polynomial divided by another polynomial. We're going to talk more about this in depth in the coming days, but for now, I want you to make a connection to something we're pretty familiar with, just the function 1 over x, or our reciprocal function. 1 is a polynomial. It's a very simple one. X is a little bit more complicated, but not a whole lot more. So 1 divided by x fits the idea of a rational function. We're pretty familiar with it. You kind of see a fuzzy picture there. We have looked at it a decent amount throughout this semester. If you don't happen to have this note sheet in front of you, I don't necessarily think you need to copy this info down. I think all the things we've talked about there with domain and range and continuity, the fact that it's unbounded, some of the end behavior sort of things, I think these are all terms that we're somewhat familiar with. We may not have used them recently, but still some good things for us to think about, and some things that we'll probably come back to later in this unit. One thing I want to add with this, though, is just talking about what's going on, in this case, at x equals 0, at that vertical asymptote. I want to talk about a way that we might describe that behavior. So on our graph, just remember that this is the positive side for x, and that's the negative side. And as we are thinking about what's going on at 0, one way to describe that using limits is when we write this notation here. So the limit as x approaches 0, but if I put a little plus right there, that means think about what's going on as I start on the positive side and get close to 0. So we have to name the function. The function is f of x. So as we start, let me get my pointer here. Okay, as I start on the positive side and I'm getting close to 0, what are the y values doing? The y values are getting close to infinity. And if we did that for kind of a same sort of idea, so we're still going to get close to 0, but now we're starting on the negative side for that same function. Okay, so now we're thinking about starting on the negative side, and as we go this way, now the y values are going down. So this one would equal negative infinity. So that's just one thing that I want to point out. That's something a little bit new. We can use that as far as notation for describing what's going on at those kind of odd places. And then we should still be aware that we can use limit notation for end behavior as is written right down there. So one of our main goals in our second example here is to think a little bit about how the graph we just talked about, or the function we just talked about, how that's going to change when we put numbers in certain places. So our main function, I'm just going to write this off to the side because it's a good idea to maybe jot down. But when we're looking at a function and we're comparing it to 1 over x, well, when we think about last semester and early this semester too, when we thought about how graphs can move around and stretch and translate and things like that, when we saw a number that was added to the x, that meant it was going left or right. And when we saw a number that was being multiplied by that x, that controlled kind of a horizontal stretch or compression. So the same thing is true here. It just happens to be it's in the denominator. So we have to be aware that we're looking for things right there to show when things have changed along the x-axis. When we have a number that's added at the end, that's going to control a shift up or down. And when we can write it in such a way that we have a number out front through multiplication, that's going to be a vertical stretch or compression. So I think a key thing here is that when we're doing these kind of problems, we do try to make a 1 appear in the numerator, and we need to separate the x out kind of carefully in the denominator. But if we can do that, then we have a pretty good idea of what is going on as far as what the graph would look like. So in our first example here, function g, it is 2 divided by x plus 3. One thing I could do quickly just to rearrange it is I'm just going to take the 2 and kind of factor it out to the front. It's going to be way in front of this fraction, and then I'd have a 1 that's left in the numerator, and in the denominator I'd still have x plus 3. So this is 2 times the fraction 1 over x plus 3. And when we start thinking about what that looks like, we could draw a little picture of it. I'm going to use some of the space from B just because I'm running out of space here. But basically what this means is the plus 3, I went left 3, and now that's going to be where I see this vertical asymptote. There is no k value at the end. There's nothing that I'm adding to it, so I have not gone up or down, just went left 3. There's no b value, so there's no horizontal stretch or compression. But I do see that 2 out front, and that means there was a vertical stretch. Well, graphically, that's really hard for us to show. So the best I can do when I compare it to the graph that's at the top of these notes is just to say it went left 3. Yes, there's a vertical stretch by 2, but it's really hard to show, so I'm just going to show this instead. Okay, and I still have a lot of the attributes of what this particular function looks like. So this last example looks a little different. We don't clearly see a 1 in the numerator or a number in the numerator, so we have to think about this a little differently. But luckily, we just finished some lessons on division of polynomials. So this is really 3x minus 7. We're dividing by x minus 2. What we're going to do is we're going to do synthetic division, and we're going to see what this division process, this fraction, is actually equal to. So I want you to think a little bit about putting this into fraction form a little bit. We have the first part of the fraction already. We have to figure out what it equals. So if I do synthetic division, I would list a 3 and a 7, right, the coefficients. And then in this little box here, I'm going to put a positive 2. It's the opposite of what we see in the divisor. Okay, and we go through the process. We drop the first idea, which was 3. Then we're going to multiply, so 2 times 3 is 6. Okay, we add those together, and I'm just noticing I forgot a symbol there. That should have been a minus right there, right? So we're going to add these things together, so in that case I would get -1. Okay, so what this means, if we think back to our last unit, we took, if I'm going to do fraction form, we took 3x minus 7, I divided by x minus 2, and the answers that I get, well, the 3 is kind of the main part of the answer, right? It's 1 degree less than what we started with. So we started with 3x. My answer is going to be 3. And then that -1, that's my remainder. So I still have -1, and I need to divide that by x minus 2. It's a minus symbol right there. Okay. And now it's just a bit of rearranging to try and get it into the form that we've looked at up above. So one thing I want to do is I want to realize, okay, the 1 over x minus 2, that's the start of my rational function. That 3, I can move to the very end of this, and I can say instead of 3 plus the fraction, I'm going to have the fraction plus 3. So I'm going to do that first, -1 over x minus 2. And then plus 3 at the end. So I'm just taking these two things and I'm flip-flopping their positions, but I should be able to do that. Okay, and after that, what I'm going to do is, well, I really don't like that negative symbol that's in the front. So I'm going to factor that out. If you want to think of factoring out a -1, that would be fine. Okay, and then I'm left with a +1 in the numerator, and in the denominator I still have x minus 2, so it's the multiplication symbol there. And then I have a +3. Okay, so all of a sudden this looks a little bit more like a rational function. We just have all these extra numbers in front. So I want to list out exactly what these numbers are telling us to do. So if we were to think about what we have here, I'm going to kind of section some things off. And just kind of keeping in mind what I'm going to write down eventually, I'm going to kind of put those things right here. Okay, if I go in the order of B, H, A, K, and there's different orders you can do that in, remember, but that's an order that works. Excuse me. There is no B value, so I'm going to talk about H. H is -2, so we're going right 2. Okay, my A value is -1. So the 1 doesn't really matter here, but the negative part does. That's a reflection over the x-axis. Okay, and then the +3, that's my k value. And that means I went up 3. So if I really wanted to take the time to graph this, and I'm not saying this is going to be the world's prettiest graph by any means, okay, but we went right 2, so normally our center of this function is at 0, 0. I'm going to go right 2, and I have to go up 3. So if you can kind of imagine this point right there, that's kind of important. That's kind of the center of this new function. What I kind of know is I now have vertical asymptote right here at x equals 2, and I have a horizontal one right there at y equals 3. And then normally we would draw in this function to go kind of like this and like that. Excuse me. But we have this a value of -1, so it's been reflected across the x-axis, which means that it's going to be a little different. It's going to go kind of like that and kind of like that, because it's been reflected across this line that's going right here. So that's kind of the more complicated version of this. Obviously, we don't see these a ton, but it is a nice little trick to know that sometimes questions throw at you. Yeah, hopefully that makes sense, and we'll stop right there.